number of girls you're putting in S is the total number of girls over 2. So now what we can do is we can put every boy who likes an odd number of girls in S as well, right? And then S will satisfy the conditions of the problem. So how many boys are we going to expect to put in S? Or let's do it like this. So say a boy B likes n girls, where n is more than 0. So for the boy, what's the probability that he likes an odd number of girls in S? So we can write this possibilities for what girls go in S, right? And then we're going to multiply this by this, where R is the number of girls that the boy likes in S. So if the boy likes 1 girl in S, there are n choose 1 ways to choose the girls. If the boy likes 3 girls, there are n choose 3 ways, and so on. Right? Everyone good with this? So what's this? I should say 2cn, because it's just the girls in n, and the girls among that the boy likes that matter. This is a well-known fraction. Yeah? Yes. This is 1/2. Another way to show that a boy has a 1/2 chance of going into S is as follows. So say this boy likes some set of girls, and then you choose some of these girls to go in S. Maybe you choose G2 but not G3 and G4. Then G1 determines, and whether G1 goes in S determines whether there's an odd number of boys or odd number of girls that the boy likes in S, right? So the expected number of boys that we can put in S is 1/2 the number of boys. So what's the expected size of S? Yeah.
The number of people in it.
Yes. I'll denote that like that. So the problem says to show that there exists a set S with at least half the students in the school. So why must such a set exist? This is a very simple question. Yeah?
Does this set with S exist? So there must be a set of more after that.
Well, it could just be that all such S have this size. So it doesn't have to be less or more. It's just the fact that if there didn't exist an S with size at least size of p over 2, there wouldn't, the expected value of S couldn't be as large as size of p over 2. Okay, let's do another similar argument with the probabilistic method. Again, we're going to use expected value on this one. So this will be example 6 in the handout. So who knows what a graph is? Raise your hand if you know. Okay, that's fairly good size. So a graph is a set of vertices with some set of connections between them, selected pairs, which we call edges. We often draw a graph by drawing various often draw a graph by drawing the pairs between vertices as a line segment and the vertices as dots. So who knows what a bipartite graph is? Okay, so a bipartite graph will be a graph that can be split into two sets such that there are no edges from a set to itself. So all the edges will be like that between the sets. So here is a graph, is a bipartite. Yeah?
Yes.
Okay. And why?
Right. And just as consisting of the vertex with one edge and the two, and then also not sure to describe the ones that are connected to the one with the three edges. And the other side just the covenant.
Yeah. So all edges in this graph are between these three vertices and these two vertices. Yeah?
So with any loop that you have, if it has even, if all the loops involved have an even number of points, then it will work as a bipartite.
Yeah. So what he said was, you can't, that this graph right here, for example, won't be bipartite because here's an odd, what's called a cycle. It has 5 vertices and it's looped. So if you put this in the first part, then this vertex won't be in the first part. So this will be in the first part, so this won't, so this will. But that's a contradiction because these two can't be in the same part. But if there are no odd cycles, the graph will be bipartite. Anyway, so here's example 6. The problem is to show that if a graph G has m edges, which is denoted like this, show that there is a bipartite subgraph H with at least half the edges. No. So here's how we'll do this. In our graph, we're going to flip a coin on every vertex, and some will turn up heads, some tails. And then we're going to just take these the tail vertices to be apart and the head vertices to be apart, and then just take all edges between heads and tails, and that'll be our subgraph. And this is bipartite by definition because all edges are between heads and tails, 2 different parts to our graph. So what's the probability that an edge is selected? Yeah? Yeah. Because, why?
Because if whatever the first one is, the other one has a 50% chance of not being.
Yeah. So if we have a vertex that's tails and it's connected to another vertex, if it's heads it will be in, if it's tails it won't. And if it's tails it will be in, if it's heads it won't. So the probability that any given edge gets put in the graph is 1/2. And so what's the expected number of edges? Yeah. So if we call the bipartite subgraph that we get, okay, this is kind of confusing, but E of H, where E, the inner E denotes edges and the outer E denotes expected value, is going to be m over 2. And why are we done? Yeah?
There has to be graph with a subgraph with n or more edges.
Yeah. Exactly. So now let's move on to more complicated examples. Actually, I'll keep this down here and move to a different board. So, let's do example 2, which is a result by Erdos, a very famous combinatorialist. So, we say that an integer, a set A of of non-zero integers, so a subset of the non-zero integers is going to be sum-free if we have no three elements of A, or there does not exist x, y, and z with x plus y plus equals z. So no two elements of A sum to another, and then it's called, if that's the case, it's called sum-free. So why are we excluding 0? Like, why wouldn't it make sense for a sum-free set to have 0? Yeah?
If 0 is in there, then it means that that it's impossible, because 0 plus any number in the set will produce that same number.
Yeah. Or in particular, if 0 is in the set, 0 plus 0 is 0. That is.
So x, y, and z are not necessarily distinct.
Yeah. I also should say in A. Okay. So Erdos showed that for all sum-free A, there is a subset of A that is, or no, for all sets A, not actually sum-free, for all sets A in the non-zero integers, there is a set B, which is a subset of A, such that B has size at least A over 3, or is it at least a greater? It's greater. So, oh, I did this backwards on my hand. I'll say for all B in that, there exists A, which is a subset of B, which has at least 1/3 of the elements, more than 1/3 of the elements of B. That is sum-free. Okay. So here's how we're going to do it. We're going to go step by step with the example 2 walkthrough. So first of all, the first step would be to find a prime P for which the elements of A are distinct mod P. You'll see why soon. And the prime should be 2 mod 3. So ignoring that it's prime in 2 mod 3, is there an n for which the elements of A are all distinct mod n?
Not
If A, okay. We will accept the resolution that infinite sets do not exist for our purposes. Okay. Now, is there a number n such that all the elements of A are distinct mod n? Yeah?
You take in large enough, right?
Yeah. So let's say that the set A on the number line, it's just between these two things. Let's say this is 0, right? So all of our elements are in A are here. Well then, if you take n to be more than this gap, then all the elements of A will be distinct mod n. Kind of like obviously. And since arbitrarily large primes that are 2 mod 3 do exist, there is a prime that is 2 mod 3 for which all the elements of A are distinct. So now what we're going to do is we're going to take this prime P, which is 2 mod 3, and I mean B. Yeah, okay, so let B bar be the set of elements of B mod P, so just the residue classes mod P. So first, we'll use the following fact. If P is equal to 3n minus 1, I claim that the set n plus 1 all the way to 2n minus 1 is sum-free mod P. Why?
Because wait, because they're all distinct.
And that's not very relevant to sum-free. That just says that it is a set mod P. Yeah? Remember the elements we're summing don't have to be distinct.
Oh yeah. Because
That's along the right lines.
Oh, because the minimum possible sum of two elements.
Define minimum mod P.
because
Yeah.
like, when you sum 2n minus 1, 2n minus 1 mod P, you just get n minus 1.
Sure.
But then that doesn't go anywhere to yes. So that's
Yeah.
That's like the part of sequencing.
Sure. And also, n plus n itself is 2n. So, yeah. So this the sum of these numbers, the pairwise sums, will all be of the form 2n plus 1, 2n plus 2, and so on, which you get from taking two terms with two n's, and n and n plus 1, and so on, until you get all the way to the two terms at the end will sum to n minus 1, and that covers every single element that isn't in this set. Yeah. So anyway, let this be equal to, or here. So let this set be S, and let A sub k be the set of k s, and the set of numbers of the form ks, I shouldn't say lowercase s, where s is in big S. So this is also sum-free for non-zero k. What fact about P do we use here? Yeah. Because if we had elements that of AK summing to one another, then we have KR plus KS equals KZ. And because P is a prime, we can divide out by K for non-zero K, because numbers have inverses, mod P. And so that just gives us R plus S is Z, which is a contradiction to S being sum-free. So this is sum-free. Okay, so now here's what we're going to do. Select K at random between 1 and P minus 1. That's all the non-zero residues mod P. And then look at size of AK, size of AK intersect B bar, which, if you'll recall, was the set of residues of B mod P. So here's a question. for random k, what's the expected value of this? So here's how we'll look at it. What does it mean for our element to be in AK and B bar? That means it's a number which is of the form KA for and B for some B in B bar. Right? And so we can write this as K equals B over S. So if a number from B, now I like it in this form more. Okay, so what's the probability that a random K will satisfy this equation for a given S and B? If I tell you what S and B are, what's the probability that K will satisfy this? There's only one value of K, right? That would be B over S, so yeah.
It's like 1 over n times the order of r.
Sure, we can phrase this question differently so that we get that, I think. Here. I'm going to do a different argument that I think will probably be easier. How to use an eraser. There we go. Okay. So, what's the probability that a random element is in AK? The size of AK, if you'll remember, is n, because this is size n. So, what's the probability that a random element is in AK? A random non-zero element. Yeah?
Wait, non-zero n over 3n minus 2.
Yes. So a specific non-zero element should be in AK with chance n over 3n minus 2. Why? Yeah. Yeah. So this is the this is the number of elements that are non-zero, and this is just the size of AK. And since AK is random in the sense that each of these will be equal to every element at some point in time, this is going to be the probability that a given element is an AK. So the size of AK intersect B bar is going to be this times B bar, because each element of B bar itself is a element, a specific element. So this is going to be the expected size, and we'll just note that this is greater than B bar over 3. Thus, since the expected size of AK intersect B bar is at least B over 3, well, first of all, why is this sum free? I mean, we know AK is sum free, right? So this is a subset of AK. So why is a subset of AK sum free? Yeah?
If it had a sum, then AK would have a sum function.
Yeah, exactly. Thus, it is. We have a sum-free. So, thus, AK intersect B bar is a sum-free subset of B bar, and we know there exists a K for which the size of this is more than B over 3. And thus, we're done if we can convert this set back into some subset of B, not B bar. But that's not very hard because B bar is the set of residues of B. So every element of B bar corresponds to some element of B that it was the residue of. And thus, this set is already, in a sense, the set which is sum free in B. And that's how Erdos works. So the set of subsets. So if S is a collection of subsets of 1 through n, such that there do not exist A and B in S with a random permutation of 1 to n. So let's take 5 numbers. So there's our permutation, and say we have our set S is maybe 1, 3, 4, 1, 2, 5. I don't know. So none of these sets are subsets of each other. And yeah, so here's how we'll define a certain event. We'll define the event E of A to be the scenario in which the first size of A terms of the permutation are the elements of A. So which of the events corresponding to these sets are happening here? Yeah? Yeah. And this is because the elements 3, 2, 4, if we look at this permutation, 3, 2, and 4 are the first few terms of this permutation, right? So in S, so what would it mean for the E of A and E of B to happen? What would this imply about A and B? Yeah? Yeah. And why?
Whatever B is, it must occur in the first B elements, and then A must occur like the A elements will be larger than the B elements.
Sure. So if we have sets B and A where the size of B is less than or equal to the size of A, then our picture is going to look like this. We'll have some permutation, and the first B elements will be B, and the first A elements will be A. But then every element of B is also an element of A, because the first B elements are also some of the first A elements, right? And so since no A and B in our set are subsets of each other, this just can't happen, right? Yeah? What? So, the point is, so A and B, if this is the case, then one of them is a subset of the other, right? But we have that our set S satisfies the property that no two elements are subsets of each other. So this can never happen for A and B and S. Okay. So that means the sum of the probabilities for A in S of E of A is less than or equal to 1. So what's the probability of EA? In terms of the size of A. So let's do an example. So let's say we have a set A of, not here. Let's say we have the set A 1, 2, 3. And we're dealing with a permutation of 5 elements. So what's the probability of E of A here? Yeah? 1/12? Close. Not quite. I don't see 12 outcomes. So we have to have we want the probability that if we choose these 3 elements out of 5 elements, that they'll be the elements of A. Yeah, 1/10. Why? Yeah. In particular, I'll write this as 1 over 5 choose 3. Right? Because the permutation randomly chooses 3 elements out of 5, and we want those to be the 3 elements of A. Thus, this must be our permutation. Our permutation will work with a 1 over 5 choose 3 chance. And in general, that means that P of E sub A is going to be 1 over n choose the size of A. Right? So we have this equation. And why should that imply that S has size at most n choose n over 2? In particular, what's the largest possible value of n choose A? Oh yeah? Okay. Yeah?
Because, like, wait,
Yeah? Yeah. So the largest possible value of this coefficient is when A is n over 2. So in particular, we can say that this is at least sum over A in S of 1 over n choose n over 2. And this is simply equal to size of S over n choose n over 2. So rearranging, we get that S has size at most n choose n over 2. And that's Sperner's. Yeah. So let's do more graph theory, because I like graph theory. I like this one. So in the graph G, we say that a set of vertices is an independent set if no element and no vertices in the set are connected. So in this particular graph, we find that I'll add some more. So we find that these vertices form an independent set because none of them have any connections. So can someone find a larger independent set? I'll label these vertices. So A, B, C, D, E, F, G, H. So F, D, and B form an independent set because they don't have any connections. Yeah?
A, B, G, and H.
Sure. So A, B, G, and H form a larger independent set because there aren't any edges between those either. In here, can someone find a large independent set? The largest I see has size 3, I believe. Yeah?
A, and G.
Sure. A, E, and G. An argument as to why you can't find 4 vertices. So A, B, C, and D are all connected, right? So you can only choose one of them. And then among E, F, and G, there's a connection between E and F and a connection between E and G. So you can't select F and another vertex, but you can select E and G. And so you can only select 2 of E, F, and G and 1 of A, B, C, and D. And A, E, and F, and A, and G in particular form that independent set. So we say that for a graph G, the independent number, or the, what's it called? The independence number is the size of its largest independent set. So example 9, this is called the Caraway theorem, says to show that this is the case. So I'll have to define these things. So first of all, when I say V and G, I mean V being the vertices in G. And second of all, D of V, it means the degree of V. And the degree of a vertex is the number of vertices it's connected to. So what's the degree of A here? Yeah. Degree of D? Yeah. Which vertices have largest degree here?
Probably D.
There's another.
Or C.
Yeah, D and C have degree 5 here because they're connected to 5 vertices each. You can see by counting the edges around them. Which vertex has smallest degree here? Yeah. Which vertices have smallest degree here? I see 4 vertices with smallest degree.
A, E, F, and G.
Yeah, A, F, and G all have degree 3. B is degree 4, and D and C have degree 5. So let's see what this says on a few graphs. So first of all, the complete graph. The complete graph is the graph where you connect every two vertices. So this is the complete graph of size 5. And what's the independence number of a complete graph? Yeah, because you can't have two vertices that don't have an edge by definition. So the independence number of a complete graph is 1. What's this sum for a complete graph? Yeah? Yeah, and why?
It's 1 plus, or 1 over 1 plus 4 for each.
Yeah. In general, so k of n denotes the complete graph on n vertices. In general, this sum for k of n will be sum of 1 over 1 plus n minus 1, because every vertex is connected to all the n minus 1 other vertices, and that's just equal to 1. So the independence number of a graph with independence number 1 is at least 1. That's nice. Here's another one. The empty graph is what it sounds like. It's the graph formed by having no edges between any vertices. So what's the independence number of a empty graph with n vertices? Yes. And what's this for the empty graph with n vertices? Yeah. Because degree of v is 0. So this just evaluates the sum over all the vertices of 1, which is the size of the graph. So let's show this.
Wait, how is the independence number of empty graph?
You can take all the vertices. That's because if you select every vertex from the graph, no two of those vertices have an edge.
Wait, but wouldn't it be true?
Why?
Because it kind of said could be a subset of another.
The independence number is the maximum size of an independent set. Okay. So anyway, let's show this. So here's how we're going to get an independent set on a graph. So for a particular graph, we'll randomly permute the vertices. And then we'll select a vertex to be in our set if it's less than all of its neighbors. For example, we'll select this vertex 1. We'll select 1 because 1 is less than 5 and 2. That's all of its neighbors. So will we select 2? Will we select 3? Will we select 4? 5? 6? So we get our wonderful independent set. Yeah?
The 1.
Yeah. What about now? Yeah. The 1, 2, 3. Yeah, so just any vertex which is smaller than all of its neighbors here, that would be 1, 2, and 3, because 3 and 2 are both less than 4 and 5 are selected, but 5 isn't less than 1 and 4 is not less than 2, right? So they aren't selected. So anyway, why does this method give an independent set? Yeah?
If 2 were connected, that would mean that they were both sort of the smallest.
Yeah. So if A is selected in the set, then A must be less than B, right? So B can't be selected in the set because B is not less than A. thus, we have an independent set. So what's the probability that a given vertex gets selected for the independent set? Let's say it's connected to d of e other vertices. What's the probability it gets selected? Yeah? Why? Yeah. So the probability that a given vertex is selected is 1 over 1 plus d of e, and the reason why is that we're selecting 5 numbers for each of these vertices, and we want a particular one to be the smallest one, right? Or in general, we're selecting 1 plus d of e numbers, and we want the chance that one of them is the smallest, a particular one. So this is the chance that a particular vertex gets selected for the independent set. So what's the expected size of the independent set? Yeah? Says the following. If we have a collection of sets A1 through AN and a collection of sets B1 through BN that satisfy that AI and BJ, well, this equals 0 if and only if I equals j. In other words, A3 and B3, for example, won't intersect, but A4 and A6 will. If this is the case, then the sum of the following quantity is at most 1. So here's how we're going to do this. So take a random permutation again of your numbers. Actually, I'm going to do another more concrete example. So let A1, A2 be 1 and B2 be 1, 2, 3, 4, 5. Okay, so why do these sets satisfy these conditions? Just briefly run through. A1 and B1 don't have any common elements, nor do A2 and B2. But A1 and B2 have some common elements, for example 3, and A2 and B1 have some common elements, for example 4. So these satisfy our restrictions. So if we take a random permutation of the elements in n, n right here I have chosen to be 6. So let's choose 3. Okay. So if we choose a permutation of the elements, we'll say that we'll define the statement E of j to be all elements of A come before all elements of B. Do any of these events happen for this particular permutation? Yeah. So this happens for A2 and B2 because 4 and 6 come before 1 and 3. It doesn't happen for A1 because 3 comes after 4, for example. So let's say we have that E of I happens. So AI in the permutation will come before B of I. So that's EI happening. I claim that EJ cannot happen for any J that isn't I. Why? Let me write down some stuff. So, okay. Yes, so so we have these conditions. So why can't it be the case that AJ also entirely comes before BJ?
So if the intersection has anything in it, that means that they share something.
Sure. So AJ intersects with AI intersects with BJ. So there's some element of BJ in here. And we also have some element here, which is in AJ by this condition. And then this element of BJ comes before that element of AJ. So that means that it's not the case that BI entirely comes before and BJ entirely comes before AJ. So we have sum over I from 1 to n of the probability of E of I must be less than 1. So what's the probability of E of I this time? In terms of size of AI and size of BI, what's the chance that all elements of AI come before all elements of BI? Yeah? Yeah, why? Yeah. So if you select the particular elements from AI and BI, say AI has size 3 and BI has size 4, and you want the elements of AI all to come before the elements of BI, let this be how they're ordered. So AI could be like here, here, and here, but in particular, what you want is that they're the first 3 elements. And so the number of ways you can take AI to be the first 3 elements of your ordering is just AI plus BI, choose AI. So this is then equal to sum from I equals 1 to n of 1 over AI plus BI, choose AI, which is what we wanted. Okay. What time is it? Or should I just continue doing them however I want? Okay. Ooh, let's do this one. So it turns out in the probabilistic method, if you want to continue learning about it, you'll see the number E a lot. It's just a thing. This will be a problem which involves E. So yeah. Example 14. This was on an IMO shortlist. is as follows. Let A be a set of the numbers mod n. It's a set of n numbers, mod n squared actually. So I'll write that as A is a subset of Z mod n squared Z, which is a fancy way to just say the number Z mod n. So show that there's a B also with size n. That is in Z mod n squared Z, for which size of A plus B is at least n squared over 2. Now what does this mean? It means the set of numbers which are of the form A plus B for A in A and B in B. So if we have a set of n residues in Z mod n squared Z, I am bad with n's, aren't I? Okay. So if you have a set of n residues in Z mod n squared, and you have a set of n residues in Z mod, and show that there exists another set of residues of size n in Z mod n squared, such that their sum covers at least half the residues in Z mod n squared. So our wonderful strategy for this is going to be choosing n numbers at random and putting them in B. So how does this do? What's the probability? Okay, here. So we'll write B plus A, union of B plus A equals A plus B, where I'm using B plus A to denote the following set of B plus A for A in A. Okay, so if we union B plus A for all B in B, we get A plus B. Fairly evident to see, because this is just all possible sums A plus B written in a different way. Anyway, what is the probability that a random element is in B plus A if B is chosen at random? So let me write this out more explicitly. B is random, fix X. What's the chance that X is an element of B plus A? So remember, A has size n, and there are n squared possible elements, possible residues. Yeah? Yes. Why? Yeah. So point is that if we say that X, okay, let's write out B plus A as B plus A1, B plus A2, all the way to B plus AN. These are n elements, all randomly chosen. The probability that X is this one is 1 over n squared, the probability that x is this one is 1 over n squared, and so on, because there's going to be one value of b giving that x. So the total sum of the probabilities is 1 over n. And so this is just equal to 1 over n. And so the probability that x is not in b plus a is what? This is a very simple one. Yay! Wow. Alright, this is 1 minus 1 over n for reasons you may see later. What's the probability then that x is not in any b plus a? And also I'm going to clarify one thing here. When I say choose n elements at random to be the set B, I'm not actually caring that they have to be distinct. Just any n elements without and with replacement. So the probability that it's not in any b plus a, the probability, let's write the elements of b as b1, b2, and so on all the way to bn. So the probability that x is not in b plus a, writing b plus a like this, that's equal to the product over all b in b of the probability that x is not in b plus a. And this is because for it to not be in any b plus a, it has to not be in every single set of the form b plus a for all b and b. And these are independent events, whether x is in each individual b plus a. So that's equal to what? Yeah. Nah. So this is the probability that a given element is not in b plus a. So what's the expected size of b plus a? Or here, just one more equation. So what's the probability that x is in b plus a? Just, yeah, take 1 minus the previous thing. So what's the expected size of b plus a? And remember, there are n squared possible values of x. Yahoo! Okay. Okay. So anyway, I'm bad at plotting. I should draw axes before drawing graphs. Okay, so this is approximately what e to the x looks like, and this is approximately what the equation 1 plus x looks like. You can prove this rigorously, but for now I'll just visually accept that e to the x is at least 1 plus x. Okay? For all x. yeah. So, what does that give here? This thing is going to be at most or at least. I think it's at least. Or am I bad? Wait, so if this is at most, oh, never mind. It's at, yeah, it's at least. So this is at least n squared times 1 minus e to the minus 1 over n to the n. Right, because this thing is 1 minus 1 over n is at most e to the minus 1 over n by this equality where you plug in x is negative 1/n. Right? And what is this simplified? Yeah? And now we will use the amazing fact that e is greater than 2. Oh, I should, yeah, okay, that's right. Okay, so this is greater than n squared over 2, as desired. This is a very frequent equality to find why we use e so much in the probabilistic method. So let's do something with variance. Ooh, fancy. So how many of you know what variance is? Yeah. I like to think of it as the standard deviation is the square root of variance, since variance is easier to define. So the variance has this wonderful expression. This is how we define the variance of the variable x. So let's process this. The expected value of x is going to be our average value of x. So x minus the expected value of x is going to be the difference between x and its average value. So by squaring it, that's saying the expected value of its square is going to be a measure of how far it tends to deviate from its average value. So in particular, if expected value of x equals 0, then we have that the variance of x is expected value of x squared, which kind of makes sense as a measure of how far x tends to get away from its expected value of 0, because x squared increases as x increases away from 0 or decreases away from 0. So, facts about variance. I won't prove these. They're not too hard to show, and I believe Wikipedia will provide proofs. But if x and y are independent, then what? Yes, then the variance of x plus the variance of y is the variance of x plus y. And here's an example of why we need this independent condition. So what is the variance of a constant times x? Anyone know? So that's not too hard to figure out if you plug it in there. Yeah?
Equals a constant times squared x.
Yeah. So this is equal to c squared x. So we can see this by simply plugging it in. If we plug cx into here, that's expected value of cx minus expected value of cx squared. And so let's pull the c out of the e. In fact, we can just factor the c out entirely to say that this is the expected value of c times the quantity x minus expected value of x. Squared. Or if we factor that out entirely, that's just c times this thing. So there's c squared times that thing, which is c bar of x. So anyway, that's that. There was a great USAMO question, USAMO, for those of you who spell it out. USAMO number 6, in fact, being the hardest problem on the test back in what year? 2012, example 16. That was very easy if you knew enough about the probabilistic method. So we'll do it. Let x1, x2, all the way to xn be real numbers such that the following holds. Their sum is 0, and their sum of squares is equal to 1. And then we'll say that for any a subset of the first n integers, we'll define S of a to be the sum of the corresponding x's. And the goal is to show for all positive numbers lambda, which are greater than 0, that we have the number of SA which are greater than or equal to lambda is at most 2 to the n minus 3 over lambda squared. Okay, so first we'll need two inequalities. There are two different things people call these two inequalities. Some people call these Chebyshev's first inequality and Chebyshev's second inequality. I use what I think is more common, Markov's inequality and Chebyshev's inequality. So Markov's inequality says the following. If we have that expected value of x equals, no, actually we're not setting that equal to anything. So if x is a random variable which is always at least 0, then it is the case that the probability that x is at least a is going to be at most the expected value of x over a. For example, let's plug in some numbers. If the expected value of x, if x is a positive variable which has expected value 1, the probability that it's at least 3 will always be at most a third. And that's called Markov's inequality. So let's prove this. So the expected value of x, its definition would be the sum over all let's say s greater than or equal to 0 of the probability that x equals s, the probability that x is equal to s times the times s. Yes, there we go. If it's continuous, replace that with an integral. So we'll split this up now into two sums. This is going to be sum of s greater than or equal to 0. The probability, or s between 0 and a, less than a, of the probability that x is s times s plus sum of s at least a of the probability that x is equal to s times s again. So for s in this range, we can simply replace s with 0 if we say greater than or equal to, because s is at least 0. And for s larger than a, we'll simply say s is at least a. So then this term goes away. And what's this term? Yeah. Because this is the sum of the probabilities that p of x is equal to x for x is equal to s for s greater than or equal to a. So that simplifies to that. And then that's what we want. Expected value of x over a is at least p of x greater than or equal to a. That's Markov's first inequality. Okay. So Chebyshev's inequality says the following. For all, what is it? Yes. So the probability that okay, here. Let expected value of x be x0 and the square root of the variance of x be sigma. The square root of variance of x also has a different name. It's called the standard deviation. So Chebyshev's inequality says that the probability that x or absolute value of x minus x0 is greater than or equal to lambda sigma is at most 1 over lambda squared. Yeah. So this sort of resembles this thing. It's a probability that something is greater than or equal to something else being bounded by a fraction. That's good. Let's show this. So the probability that x minus x0 is at least lambda sigma. If we square that, if we square the inside thing, that becomes the probability that x minus x0 squared is at least lambda squared variance of x is at most 1 over lambda squared. Yes. So this is exactly in this form, I claim. And that's because we can plug in, if we set a to be equal to lambda squared variance of x, variance of x, and instead of x, what we plug in here is we set, okay, this is going to be, if we plug in x prime into this equation where x prime is equal to x minus x0 squared, well, the expected value of x prime by definition is variance of x. So that gives exactly this, because this is equal to lambda squared, variance of x, there we go, variance of x over lambda squared variance of x. So those are Markov's inequality and Chebyshev's inequality. And so now we're ready to attack this problem on the left. So here's how it'll go. We're going to flip n coins, and we're going to say xi is equal to xi, this is capital X, this is little x. So this is going to be xi if ith coin is heads, and this is going to be 0 if ith coin is tails. Okay. So first of all, what's the expected value of xi? Yeah? Yep. Cool. And what's the variance of xi? Plugging it into there. that's a little x, that's a big X. So what's this? Well, if we get a heads, this expression is going to be little xi over squared over 4. And if we get a tails, it's going to be the exact same thing. Right? Because this is, if this is heads, the term being squared is xi squared, xi over 2. And if it's tails, the term being squared is negative xi over 2. So this is going to be equal to x. Yeah, this is going to be equal to xi squared over 4, where this is a small x. Okay. So now here's how we're going to define A. Let A be the equal to the set of I where ith coin came up heads. So first of all, A is chosen randomly entirely because it's chosen by coin flips. So what is S sub A in terms of x sub I? S sub A being this sum for I and A of x sub I. So in terms of capital X sub I, what is this sum? So if we're summing xi over all the heads, that's exactly summing up capital Xi. Because this will just add 0 for all the tails coins. So what's the expected value of S sub A? Well, since SA is the sum of all the x sub I, that's going to be the sum of the expected value of xi. And we know expected value of xi is xi over 2, little xi over 2. And what's this? It's given by the problem statement. Yes. Now the variance of S of A, so we know, so all of these xi are determined by independent coin flips. So by that rule about summing variances, the variance of S sub A is equal to the sum of the variances of x sub I, which, as we have right here, is xi squared over 4. Yeah, so it is 1/4. Because the sum of all the xi squared is equal to 1. So let's use Chebyshev's inequality on S sub A. So we have that the probability that S sub A is greater than or equal to, what was it in the problem? Lambda. Well, first of all, I claim that this is equal to 1/2 the probability that the absolute value of S sub A is at least lambda. And here's why. So if we have, in terms of S sub A, what is S sub A complement, where A complement is simply the set of coins which came up tails instead of heads. Or here, what's this? It's 0. And this is because this is simply just summing up all the coins. Sum of x sub I for all the coins which came up tails, plus sum of all x sub I for all the coins that came up heads. That's going to be sum of all the x sub I, and that gives 0 by the prom condition. So we have that S sub AC is equal to negative S sub A. And thus, the reason that this is 1/2 of this is because it is equally likely for S sub A to be at least lambda than it is for it to be at most negative lambda. So, what do we get if we plug in stuff into here? So first of all, what is sigma? That's the square root of the variance of S sub A, which we know is 1/4. So sigma, the standard deviation of S sub A, is going to be equal to 1/2. So what is x sub 0, the expected value of S sub A? We have that right here. That's going to be 0. What else do we need? We need a value of lambda. I'll just leave that open for now. So let's say lambda equals A. So then this probability is going to be at most 1/2 times the times what? 1 over. Oh, I don't need to leave it open. Okay, so what lambda should we plug in? What lambda should we plug into here to get this lambda? What? Yeah, lambda over sigma. Yeah, so 2 lambda. So lambda prime equals 2 lambda. And so that gives us that this chance is going to be at most 1/2 times 1 over 2 lambda squared, which is equal to 1/8 times lambda squared, and 1 over 8 over lambda squared. Yes. And so what are the total number of sets A? 2 to the n, right? Because they're just 2 to the n sets. So thus the number of SA which are at least lambda is then equal to 2 to the n over 8 lambda squared, which we can rewrite as 2 to the n minus 3 over lambda squared as desired, because we wanted the number of SA, which are at least lambda, to be exactly almost that. Okay, so let's do, yes, I like, so I'll start from here. Let's do more graph theory. So we are going to be looking at two things called the chromatic number of a graph and its choosability or list chromatic number. So the chromatic number of a graph, denoted chi of g, so is going to be the smallest number of colors we need to color it, and color its vertices, so that any two adjacent vertices have different colors. And so when we're writing colorings down on a board, we often use numbers for the colors. So let's say 1 is red, 2 is yellow, 3 is blue. So here is a coloring of a graph. It satisfies, again, the property that any edge connects vertices of different colors. Chi of g is going to be the smallest number of colors needed to color such a graph. So what's chi of this graph? The chromatic number of this graph? Y3.
Take any vertex, declare that as 1, and then the rest of the state, 3.
Sure. And why can't it be 2 colors? Yeah?
Because there's an odd number, so it will end up, if you go around numbering it with only 2 colors, then it will end up without 2 of them right next to each other.
Yeah. Okay. So chi of this graph is 3. What is the chromatic number of a bipartite graph? Well, usually, what is it? Yeah. Is that hand or not? Okay. I assume this gesture means 2. Okay. Yeah. The bipartite graphs, by definition, have chromatic number at most 2, because they satisfy that if you color one part red and the other part blue, all edges will be from red to blue. So that's a chromatic number. The list chromatic number, denoted ch of g for choosability of g, is going to be as follows. So if we have a list of possible colors that we can use for every vertex, I'll draw this a different way. So if we have a list of possible colors to use, so right here I'm going to give this thing 1 and 3, maybe 2 and 4. Let's give this thing 1 and 4, 1 and 2, 3 and 2, 3 and 4. So I've just assigned a list of possible colors to every single vertex, with each list having 2 in length. And so a list coloring of this graph would then be a way to choose colors so that every vertex is colored with a color from its list. So first let's do a simpler example. The list chromatic number will then be the minimum number of colors you need per list to guarantee that the graph is colorable. So the list chromatic number of this graph is 2, because you can't color it if I tell you must use red on both vertices. But if I give you at least 2 colors for each vertex, you can always choose a color like green and red right here. So, can you find a list coloring of this graph with the lists I gave? Why not?
Choose one of the vertices of 3, 4, one on the left.
Sure.
If you choose either 1 or 3, then they'll force corresponding pair sets. For example, if you choose 1, then it'll force the top 2 vertices keys to be 4 and 2, and then you can't color the other one with degree 4.
Yeah. So I'll repeat the argument. If you color this with 1, then these 2 vertices must be colored 4 and 2 because they can't be colored with 1, and then you can't color this vertex. But if you color this vertex 3, you can't choose colors here or here. You have to choose 2 and 4 here, and then you can't choose this one again. So the list chromatic number of this graph is more than 2. In fact, it's 3. So yeah. So claim. Well, first of all, I'm gonna do some basic facts about chromatic numbers. Here. Huh? Oh, okay. In that case, I'll cut this short and give an excellent statement and not prove it. But anyway, fun things. So this right here, anyone have an idea why it's true? Let's say I've colored a graph. With chi of g colors. What's a upper bound we can place on the number of vertices colored 3? 2, sure. In terms of this thing, it's just this thing. Because by definition, any vertices with the same color, and the set of vertices with one color must have size at most the independence number of g, because they form an independent set by definition. So this is a fun fact. Stuff are related. We also have that the choosability of g is at least the chromatic number of g, and that's because if I simply assign the same list to every vertex, the challenge for choosability is to color it with different colors on every vertices with the same possible set of colors, which is by definition the chromatic number of g. Anyway, with the probabilistic method it can be proved, although I guess I've run out of time to do that, that this is the case. Which you might be able to do if you follow it on the handout in example 12. It's a very neat result. Anyway, I guess that's all. Hope you enjoyed.